Cool.
He's over there, yeah.
Okay. Oh, looks good though.
All right,
Thanks.
Yeah, see you later.
See you. Hey, how are you? Hey, good morning. How are you? Hey. Okay, School of Mines there. Doesn't look like anyone's over there at School of Mines, but maybe.
Yeah, I'm here.
Oh, okay. Oh, you're sitting in the far corner or something, I think. Okay, at least there's someone there.
Yeah, I'm sitting closer to the projector. I don't think he can see me on the camera.
Yeah, I think I can see an arm, but anyway. All right, so I sent an email over the weekend, maybe on Friday, right about correction or modifications of the first homework. So was that clear, what I'm asking for? So now the homework consists of just the first problem of Peskin, which is basically classical electrodynamics, and then also filling in some of the details in one of the first steps for promoting things to quantum variables. So basically, just in case that's unclear, so this is homework 1. Problem 2. So this involves basically filling in the steps going from equation 2.8, which is basically the classical version of the Hamiltonian, filling that in to how you get equation 2.31. In particular, the last line. This has two lines. I want to stress that because the first line is sort of, by definition, you're just inserting things for the first line. The last line involves some more work. So don't try to finagle your way out of it by just doing the first line and then saying you got the answer. All right, any questions about that? Okay, so it should be more doable. I noticed that the second problem, we'll just hold off for another problem set because it's a little more involved. We probably won't go over everything that's necessary for doing that problem. All right, so we basically ended last time with a review of classical field theory and especially talking a lot about Noether's theorem last lecture. We had various examples. So now we're going to finally turn on quantum mechanics, really make things quantum mechanical. So this is really now starting section 2.3 of Peskin. Section 2.3. I don't know how these markers go bad this fast. Just start. This is called canonical quantization. Does that look better than the black? Probably, right?
Yeah.
So we'll call this canonical quantization. Sometimes people call this second quantization. But basically it's just a souped up version of what we know about the prescription. So in particular, right, if you took quantum mechanics with me last semester, you remember, right, we had these postulates for how you go. What are the postulates of quantum mechanics? If you had to boil it down into a few things, and one of them was sort of one of the core elements was, right, take your classical Hamiltonian and you write it in terms of the canonical variables, these these non-operator entities, Q's and P's, basically Hamiltonian dynamics, that obey Poisson brackets in the old-fashioned classical world. And we promote those Poisson brackets to commutation relations, and we get out quantum mechanics. So that's basically the same thing we're going to follow. So, right, we'll take our Hamiltonian, in terms of Q's and P's, and promote them to operators. Operators in particular that satisfy canonical commutation relations. So that's what we're going to do. And the take-home message is going to be that the Klein-Gordon Field is a superposition of simple harmonic oscillators. So there's a famous quote that, in your early years, when you're learning theoretical physics, just involves learning various increasingly abstract versions of the simple harmonic oscillator, which is largely true, right? And that really is, at the end of the day, all that the scalar field is. So, right, the take-home message is actually the title of this section. I don't know if this marker is going to make it. That the Klein-Gordon field Klein-Gordon scalar field is a set of simple harmonic oscillators. So let's understand what that means. So when we were considering discrete systems, back in non-relativistic quantum mechanics, the way we basically summarize the building blocks for discrete systems, that's really what we were studying in non-relativistic quantum mechanics. It's not something continuous like a field. Right, the important things to remember, right, is you have these, I might have various Q's and P's, but those commutation relations, which in our old notation, right, we always put hats on things to make it clear that these were operators. They're not just ordinary boring numbers, but things that do an operation. We're going to drop that now because it gets too tedious writing out hats all the time. But this will obey the commutator that it's zero, right, if these i's and j's are not the same, and it's equal to I or IH bar secretly, right? Because we remember, in our old-fashioned way of writing things, x comma p was I H bar, if that's really px, right? But now we're just gonna summarize it as just being equal to I. If it's the same variable, then the q's, no matter what they are, those are 0, those commute. Got commuting space, and momentum also doesn't care about the order. So those relations basically summarize what we impose for our dynamical variables. And so we're just going to boldly extrapolate from discrete systems to continuous ones that they should, let's see what happens if we impose that they have basically the same sorts of relations. With now a field operator sort of playing the role of position. So I'm going to omit hats, right? It'll be clear, right? We're doing really quantum mechanics now with canonical quantization, so these guys are really operators. So for continuous systems, it'll be very similar. Impose phi evaluated in phi will be something that could depend on the location for sure. So we have phi and also the momentum canonically conjugate to phi, sort of equivalent thing of p for our field theory. That'll be I. And instead of a Kronecker delta, right, will now be a delta function, the natural continuation of this discrete object of this continuous world. And everyone else will be 0. So phi evaluated at 2 points, that'll be 0, and so will the momentum. All those commutators are 0. So the first, remember it's back to the good old days of just Q's and P's. So what would our problems usually consist of? They usually consist of, write down the Hamiltonian and then determine its spectrum, solve the eigenvalue problem. Once you know that, you kind of know everything, because you can build up any solution out of the eigenstates. So let's try and think sort of along similar lines for our first steps into quantum field theory. But backing up, actually, before we even go to this world, something we could do, and that we did do in quantum mechanics, right, is Fourier expand something. Often will help. And I want to write down sort of just a classical Fourier expansion we'll compare with in a minute in the quantum world. But classically, we write down this Fourier expansion for the field in momentum space. And it's often a useful trick to do this. You can simplify your equations depending on what your Hamiltonian looks like. So instead of my expansion being a sum, right, it's got to be some infinite, the equivalent of a sum. It's an integral. So this is really just the Fourier transform of our spatial field. Now we can just think of it as being something that has components, right, in momentum space. Right, and sort of as you expected, we insert this into the classical equations of motion. Insert those into the EOM. So remember what that was. It was this d mu phi plus m squared phi. That's 0. And it's going to be, we can break up just And now, right, when I do a spatial derivative, right, there's only one place where x appears on the right-hand side, right? So if I do a spatial derivative, that's equivalent to bringing down an IP. So when I want to do that twice, an IP squared would just be p squared with a minus sign. So, right, this is still acting on 5x. Right, this is 5x, 5x. So right now, if I do my Fourier expansion, now I'll really insert this equation. All that's going to come down will change this one term. So I'll instead of dt squared plus p squared, the total length in the spatial direction, right, of momentum. 5 p now plus m squared 5. Right, so I could think of this as sort of the equation of motion each of those momentum modes got to obey. So it's really also now, right, even if they weren't going off before, alarm bells should go off now, that thinking of this as a simple harmonic oscillator is reasonable, right? I mean, this is exactly the same equation of motion as a simple harmonic oscillator, same DOM or an SHO. Simple harmonic oscillator with frequency omega p square root of p squared plus m squared. Okay, again, before we really delve into what this implies for fields to impose canonical commutation relations for them, let's remind ourselves of some of the details and some of the formalism we used for the simple harmonic oscillator. I remember what was the best part of the simple harmonic oscillator in quantum mechanics. I mean, not all problems can be solved as easily as they can for the simple harmonic oscillator. But what was sort of one of the nice features?
The raising and lowering?
Yeah, that you could do this raising and lowering operator trick. So let's remind ourselves what that was about and how we did that. So, reminder. So, okay, so our Lagrangian and our Hamiltonian, either one, right, that we're talking about for our Klein-Gordon field is also strikingly similar, right? So let me now go to back to the non-relativistic quantum mechanics world. Let me call phi. I can use the same label, but I'll call it my space coordinate. So just to draw the analogy even closer. So before, what we were writing were things like 1/2 m v squared, or phi dot squared, right? And minus 1/2 m omega squared phi squared, right? Stuff like that. Which looks very, very similar to what we had for our Lagrangian in quantum field theory too. Instead, we have something with a 4 derivative instead of just one time derivative. And we also have instead just a m squared phi squared, but all that's, just coefficients basically. We could define coefficients however we want. But at the end of the day, the thing's quadratic, so it's very, very similar. And in the Hamiltonian formalism, we use our same prescription to switch variables to momentum, the canonically conjugate momentum to phi, and instead of 1/2 m omega squared phi squared, we get a minus sign, like we usually do. We switch from Lagrangians to Hamiltonians. So this guy is p phi d m phi phi. Right, and like we were saying, the nice thing in quantum mechanics is that you can rewrite, right, to make connection. Also, right, we also have for this, for our variables, our space and momentum variables, which is ultimately, physically, right, this is the manifestation, the most sort of abstract version of the uncertainty principle. It implies the uncertainty principle. And we can rewrite in better variables, or better operators, in terms of these guys, A and A dagger, which we call annihilation and creation operators. So in terms of my original variables, phi is square root of h bar over 2 and omega, A plus A dagger, and p phi is square root, I guess it's over I. 1 over I square root of omega h bar over 2 and other linear combination A minus A dagger. So right, we can solve for what, if we impose this as our commutation relation, we can solve for what property A and A dagger have to have, for what their commutation relations have to be. They have a really simple one to remember, which is convenient. And the very helpful fact from this is that you can really show that if you're an eigenstate, to have one eigenstate, call it P or something, label for the eigenvalue. If I start out with one eigenstate, if I multiply that eigenstate by A or A dagger, it's also an energy eigenstate. That's the great thing. So that's why we call them ladder operators. If you start out on the ladder, you'll always be on that ladder. So you can always, if someone gives you one of the elements on that ladder, you can walk up and down the ladder by just applying A and A dagger. You can fill out the whole spectrum. So that's what's great about it. So this really comes down to the fact that, right, so you can use this to rewrite a Hamiltonian. So Hamiltonian with a simple harmonic oscillator, h bar omega, A dagger A plus 1/2. So this 1/2 will also appear in quantum field theory and be slightly more confusing when it appears in field theory, but right, for now, right, this is the expression we get. Just basically, we interpreted this too, right? We would also sometimes define this object, this A dagger A thing, to be the number operator, the thing that counts how many quanta are in your state, right? Because this equation also says that the lowest rung of the ladder is 1/2 h bar omega, and it goes, each rung goes up by in units of h bar omega. So I could interpret this thing as adding particles. Right, so we define the vacuum or the ground state as the thing that's destroyed by A. It has energy 1/2 h bar omega, and right, we can fill all of the states. The whole spectrum. Fill the whole spectrum. Determine, I guess. Spectrum. In particular, right, using, this is what I want to claim, and we'll actually do it because it's quick, and we're going to use it again. So the crucial thing you can use to verify this are these relations. So these are easy to verify once you make this transition to annihilation and creation operators. So now I also have H in terms of the A and A daggers. So I could easily check this. We're not going to check it, but it's very straightforward. Well, let's just check this claim that we can determine the whole spectrum this way. Also, just for this reminder of how this whole story works, and we'll use it again. Feel free. Are there any questions so far about this quick review of the simple harmonic oscillator? So let's verify that, right, I said in words, right, if I start out with some energy eigenstate, is it true that a dagger of that energy eigenstate is still an eigenstate? So let's check. So we'll check that if E is an energy eigenstate, so it is, in this case, I'll check A dagger. Not at the same energy, of course, but still an energy eigenstate in the Hamilton. It doesn't take you to have some non-eigenstate. So in particular, right, the way to check it, how do we go about checking it anyway? How do I check that? If I hand you something and say it's an eigenstate, how do you check it? It's actually not too hard, right? What do? We could review eigenstates, but I assume we don't need to do that.
Just operate on it and see if you get a multiple of it.
Yeah. So if it's not, there's a way to think about it. How do you show it's not an eigenstate? How do I prove the opposite? If I gave you an eigenstate, you apply the Hamiltonian to it, and it becomes some new state that sums, you can't, it's just not an eigenstate. I mean, that's the other way. So anyway, let's just do it, right? So we do H acting on A dagger E. And now I'll make use of this property. So this tells me how I can, because what I really want to do is have H act on E, because I know how that works, right? Because the assumption is H acting on E gives me the energy back and doesn't change the state, right? That's what it means. So what's nice is that I could use this relation, right? So this is equivalent to saying H A dagger minus A dagger H is equal to omega A dagger, right? So if I have H A dagger, that's the same thing as having A dagger H plus omega A dagger acting on the same thing, right? So that's great because this thing's just a number. This is now to the left, so I don't have to worry about him when I go for our first pass. What happens is for the first term, right, I have A dagger H acting on E plus omega A dagger acting on E. So I already know how what this looks like, right? This is a E state. This is omega A dagger acting on E. So now I can just, like these things, this omega and this E, those are just numbers, right? So they don't care about order of anything. But overall, I see the thing that it's proportional to, that both terms are proportional to, is an A dagger E eigenstate, right? So I can write this, I can pull out the E plus omega, have that all be acting on the A dagger E. So it gives you even more information, right? Not only says you apply H to this state A dagger E, and you get back A dagger E, it also tells you what his new eigenvalue is. So this does have the action of creating some moment, some energy, right? It's raised it exactly by a quanta of omega. So the two take-home messages from that, right, are this is indeed an energy eigenstate. And has energy That's why we call that A dagger thing the creation operator. Created some quantum of energy. So we can do exactly the same thing with this relation, right? If we wanted to answer the question, what's the energy associated with A acting on B, rather than A dagger, right? So it's all exactly the same steps. You find out instead it's E minus omega. So that's why I was saying, right, you start out with E, you can lower with A, right? It's the lowering operator. Go down E minus omega and so on until you get to the ground state. Or you could go from your whatever rung you're starting on and repeatedly apply a dagger to fill up. And this we can go infinitely far. That's how you fill in the whole spectrum. All right, so hopefully that's review for everyone. If it's not, it might not be, in the right class, really. I mean, because this is sort of like one of the sort of core things in the first semester of quantum mechanics. But anyway, any questions about this? All right, so let's go on now back to our main topic, right, which is the field. How do we make a field quantum mechanical? So we're going to use two of the same things we just talked about. First, we'll do a Fourier expansion, and then we'll interpret the coefficients as canonically commuting operators. So now let's do, this is the free scalar field. So for today, right, we'll stick with a real scalar field, but I think on Wednesday I'll talk a little bit too about the complex scalar field, and we'll see already how we get antiparticles and things like that. So, right, now we're going to apply the same quantization procedure. To the Klein-Gordon field, or to the free scalar field. Right, so we'll treat phi and also pi, momentum associated with the field, as the sum of annihilation and creation operators. So we're going to expand the momentum, expand just the field in momentum, just like we were doing before classically. You could always do that, so Fourier expansion. Now we have a special coefficient associated with Lorentz and rates we'll talk about. And things that look very familiar in an analogous sort of thing for conjugate momentum. Minus I over omega p over 2 AP pi px minus AP dagger e to the minus I px. And I won't write it out all the time, right? This px is really a dot product of three vectors, right? But really it should be p arrow dot x arrow, but that's one of the arrows for right. So. All right, so these sorts of expressions have a lot of writing involved, especially if you want to check that anything is true. That's actually what that second homework problem is all about. getting you familiar with doing it yourself a little bit. But let's check that. So, with these annihilation and creation operators, we'll have AP, a Q dagger, that's 2 pi cubed, and a 3 L. So an obvious question is, does this imply that these are really canonically commuting, right? Does it imply that we have that sort of analogy that we had, this analogy with the simple harmonic oscillator? In the simple harmonic oscillator case, right? This was the same statement ultimately as the fact that X and P were I H bar, that their commutator was I H bar, right? So a key question is, will this imply, let me see, call it star thing. So the question is, does star imply that phi of x py would imply that that's I delta function? So it seems kind of burdensome to actually do, right? But that's what we're going to do. It's not as burdensome as you think because of this relation. So let's write it out. It'll be very big, but it will simplify very quickly when we write everything out. The other key thing, there's also some relation between that the field has to obey for this thing to be real, even though we're expanding it in this complex way. But we won't go over that right now. But the important thing to emphasize here is that, right, whenever you do this expansion, think of P as fake, right? I mean, it's whatever letter you want, right? It's just an integral, it's a dummy index. And you have to be careful when you have an expansion of one guy times an expansion of another guy, because their two dummy indices are not the same. You don't want to write them as the same, because if you do, you'll get confused. They're secretly different, so keep that in mind when you do that. So now let's just insert this expansion. I don't know what I'll call it. Well, insert Fourier expansion. Into a commutator to check what is the commutator of phi I. So, and actually, just to make it clear, let me even just rewrite on the board. I'll rewrite that says phi evaluated at the position y, and I'll also change his momentum integration. The next best thing in P for momentum is Q. Everywhere there's a P, there's really a Q. And remember, right, you're always free to do this. You could call it P1 and 2 or something if you wanted, or P and P prime. And there's. Okay, so I think everywhere I switched. So now we're really going to just use these two expressions to insert into the commutator. So let me write that down. Write it out far to the left so we have room. So right over P, 2 pi cubed, P3 cubed, 2 pi cubed, a minus I. They both have the square root of 2 under, so we'll have an overall 2. And this guy is upstairs, omega Q, and omega P is downstairs. And now we'll start organizing commutators. So I'll have terms like IPX times a minus IQY. That's how I want to group things. So, in particular, right, I'll have minus a P, a Q dagger times e to the I px minus I qy as one term, and the other term I'll just write below. We'll have a P dagger a Q times e to the minus I px plus I qy. Does this make sense? What we're doing? So now, this is the line that looks the worst, because it's going to simplify very nicely, because this is secretly a delta function, right? So this will also get rid of one of the integrals right away, right? Because the only place this thing will have support in this integrand is when P and Q are the same. So we can carry out the D3Q integral. We'll get 5x, 5y. So, right, really going to use this thing is 2 pi cubed times 3 delta function, p minus q, and the minus version of this down there. So this will give us, once we carry out that D3, Q integral, will be that this only leads to the integral over P. We have a minus I over 2. This is a minus 1, and this is a plus 1 now. We have e to the minus I, P, and Q and P are the same again, right? So now the exponential 2 simplifies it down to just I, P, x minus y, and minus I, P, x minus y, or y minus x. Right. These are actually the same thing. Those two exponentials. These two terms are the same. So overall, right, the 2's will go away, and the minus sign will go away. So we'll be left with 5x by y.
Why are they the same?
Did I miss a minus?
Or is it a minus 7?
Let's see. Right, was this right? let's go back one step. Yeah, I think that looks minus sign during the previous part. Yeah, I'll have to go back. I don't really, it doesn't seem like there was any stuff here though, right?
Yeah.
Hard to find. Yeah, I think they must have just made
Is there from the computation relation, the computation of a b equal to minus computation of b, and we can change the exponential.
sorry, what? Sorry, say again. This?
The second one, yeah,
This one?
yeah.
This should really be what?
The from the computation a b equal to minus b, yes, and the dragger from that we have the complex conjugate and is the real one, so we can change that.
Oh,
variable.
yeah. So you're saying the reality condition?
Yeah.
Yeah, sorry, I think that's right. Yeah, should have, right. So right, there is this condition that we have to apply that I glossed over, that we have to have phi star p equal to phi minus p
Yeah.
for this thing to be real, for phi being real. Right, sorry about that. So this will finally become d3p over 2 pi cubed with a plus I and a e to the I dx minus y. So this is almost something really simple. Turns out to be even simpler than what it is already, from the fact that there's a nice maybe even sometimes taken as the definition of the delta function, which is that you can write a Fourier transform, for example, on 1D. Here we really have it. These are all three integrals, right? But in 1D, there's a nice relationship between exponentials and delta functions, which is this. Sorry, dp. So this secretly is actually a delta function in 3 space because of this this identity, right? I can reinterpret this exponential. Remember again, p is some dummy variable. It's not really, it doesn't show up at all on the left-hand side. So it's not so surprising in the end. You have some equivalent expression where p doesn't even appear. We get finally out the correct thing that we sort of expected, which is that phi and p are indeed canonically commuting variables. So the next important thing to tackle is the Hamiltonian, but that's your homework. Homework. So I want to talk about the final result though. It's your job to do the computation, but I'm going to talk about how we interpret that result, because the result is weird. All right, so you're going to show, and you will show that H can be written as, again, the sum harmonic oscillators, omega p, A vector A, 1/2 AP deck. So you can show that just from the classical expression of just following the same prescription. You take the classical expression for the Hamiltonian, now you make phi and pi canonically commuting variables, and you can get that. It involves similar sorts of steps to what we just did for showing them to get this commutation relation. But this is really weird, right? Because we already know what this thing is from our annihilation creation operators, right? This is equal to 2 pi cubed. These are the same, the annoying part is that these are the same momentum, right? So that should be delta evaluated at 0, which is otherwise known as infinity. So that's strange. We have infinity. So there's something weird going on. So this involves a small detour that I wanted to do to just talk about the vacuum, because it's subtle and can be confusing. So talk a little bit about the vacuum in quantum field theory. So there are a lot of infinities that will come up in quantum field theory. And there are different ways of dealing with them, so I wanted to talk about, to give you a flavor a little bit of what's to come, and also how we'll basically sidestep this issue for now. But so it looks also somewhat similar to what we had in a way of rewriting the Hamiltonian just for the simple harmonic oscillator, right? There was a piece similar to this. So it's basically just saying, I can think of this as a number counting operator, so I just can compute what's the total energy by counting the number of quanta I have of momentum p, and they each get an energy omega p, and then I just sum up overall space. So actually I'm going to get infinity again, right? Even if I ignore this first infinity, I'm going to get infinity again because I have an infinite number of modes to integrate over. So it seems doubly confusing, right? So first let's talk about what we mean by the vacuum in quantum field theory. But basically, we'll think of it as the analog of the ground state in non-relativistic quantum mechanics. So we'll define the vacuum as the state that's annihilated by the annihilation operator for all possible values of p. Thing that gives you 0 back for all p. So that ground state energy, I apply the Hamiltonian on the vacuum. I'll just call this E0, E naught. So that's nice because this, the omega p, if I'm talking about a massless field at least, oh yeah, sorry, I don't even have to worry about this state for the ground state, right? This will be 0, this is a number counting thing. So the first term will be 0, so my total energy will be this d3p, omega p over 1/2, and d3 of 0, acting on the vacuum state. Right, so this 2 pi cube cancels that 2 pi cube, and I have just a 1/2 and a omega p. So right, so this isolates the first infinity, which says even in the case of having the smallest amount of stuff you could have, the vacuum thing, the state that's always annihilated by all the annihilation operators, even that's going to be infinity, right? This is the first infinity. This one is slightly less serious. This is a type of divergence called an infrared divergence. It comes from a long distance behavior of what we're doing. Right, so by the way, another sort of aside about infinities. So usually when they appear in quantum field theory, they appear either because we did something wrong or because we're asking sort of a wrong question. So we'll see sort of examples of both of those. So for this first infinity, secretly comes from considering infinite states. So instead of considering infinite space like we're secretly doing here, let's now imagine instead, would this thing still persist if we put everything in a box? So what we could do instead is take our 2 pi cubed d3 to 0. I can use this identity again. How do I think of delta functions? Delta function's sort of a funny object, right? Someone who's 0 everywhere except for one place where he's infinite. So that helps to have prescriptions for how to think of him. So I want to instead, what I'm going to do is imagine put everything in a box and then take a limit. But, like L. Going to infinity. And this is certainly allowed to do this. Think of it. This is just using that identity we had from before. The Fourier transform of a delta function is an exponential. And I'm going to be interested in the value of that thing at p equals 0. So, but let's stare at the right-hand side of that. P is 0, that is just d3x. So it's just proportional to the volume, right? It's an integral over d3x. So let's, we could work with finite volumes if we want, or so minus L over 2, or L over 2. So this is really just going at the volume. One thing you could do to make life less confusing is just think about energy densities, for one. And if we just rid of this infinity, by looking at just energy densities. We'll call that epsilon, curve of E. We'll just consider E naught over V. So this epsilon thing then will just be E3P on that to make a P. But right, this is still infinity. Right, because I have an infinite, because I think because P is going to infinity. So this kind of infinity is a little more interesting in the sort of the way that we think about them now, the modern way of dealing with them is to say that you get infinity because you're overly ambitious. It's our fault for getting infinity because we suppose that this theory that we wrote down makes sense to arbitrarily large momentum. Remember, from an empirical point of view, right, we've only explored momentum up to tens of TeV at the Large Hadron Collider. Right? We have some finite limit of understanding how the world really works. So it's sort of our hubris, it's sort of our arrogance that leads to that divergence. So at first, people spent a lot of time, decades, thinking about these conditions before they realized that quantum field theory is, you can view that problem in a more positive way as a way of telling you that the theory is limiting sort of its own applicability. It tells you when it's going to start breaking down. So this shows up in other field theories too. Sometimes more explicitly, you'll know exactly when it will break down. But roughly speaking, right, we shouldn't expect the theory to be accurate to arbitrarily large energy scales. Arbitrarily large momentum or energy. So this is connected with something called effective field theory. So in the 60s and 70s, people really finally understood the right way to think about quantum field theory is really having a domain of validity. And at the end of the day, none of your observables, at least at low energies, should be dependent on how you treat that infinity. So really what you'll do in the end, if we're saying that our theory can't be valid at arbitrarily large energy scales, what we'll do is introduce a cutoff to make things finite. We're not going to do that yet, I'm just telling you what the story is, since these infinities were really confusing for a long time. So instead of considering integrals like that, we'll consider integrals like 0 to lambda, where this thing is some cutoff, which none of your low energy observables can depend on. At least for normalizable things. So, but this is all that we're going to do. So for now, what we're going to do instead is, for this second infinity that we encounter, the way we will treat it instead is to ignore it, because what we're going to do is look only at energy differences. So, we'll only consider energy differences. We don't care about the energy with respect to the vacuum state, because it's not a good way for us to measure that. We're only going to measure energy differences. So we'll basically ignore the infinite energy of the vacuum. So what that practically means is that the definition for the Hamiltonian we'll really use is this T3P 2 pi Q. This is really, of course, the Hamiltonian density. I should describe that. One of those. Okay, so that's all I wanted to say about the vacuum. The first two infinities we found. But we can define, if we stick with our definition that we're going to basically define with this another practical sort of definition, that this means then effectively what we're going to call, is we'll always be referring energy with respect to the vacuum. Maybe it's infinity, but whatever it is, we're going to call that thing 0 because we're only going to measure energy with respect to that state. It's not really infinity because we introduce this cutoff and all that, but we're not even going to go that far right now. We're just going to ignore really want to understand the details of this infinity story, that's sort of the second part of the book. The book's sort of roughly divided into 3 sections. The second part, which is the whole semester basically, in its own right, deals with all of the subtleties of these infinities, and that's called renormalization. Right, but so starting with this vacuum, right, we can also verify the same SHO relations. Are super helpful. Things like H A dagger is omega P, P dagger, and H A minus omega P. So in the same way, right, because it's exact same relations are omitted, we have the same form for the vacuum energy. We can build everything up, right? Same, what it means is if I start with the lowest rung, I can add some momentum to it by inserting a creation operator, the A dagger. So I'll also define my momentum eigenstate same way. Call this guy the thing that happens after I apply a creation operator to the vacuum. So just like we used these before in non-relativistic quantum mechanics to check that this will be an eigenstate, we can do it again. It's all exactly the same steps, right? I want to check what's the energy of this thing. Is it well defined? Is it really an eigenstate? And what is that energy? It would be exactly the same steps. Do it super quickly. It's really, literally the same thing. Again, now HAP, exactly the same thing. Omega P, AP dagger plus AP dagger H. All that acting on 0. That thing I'm defining away to be 0. When H acts on 0, gives me back 0. So I get back omega P, AP dagger, acting on 0, which is P, right? So it really has the right form. And remember too, what was omega P squared? It had to follow the right form for a relativistic particle mass. Had to be P squared plus M squared. Which already starts looking suggestive too, that I can think, just like we had a simple harmonic oscillator, right? This is some discrete object, right? I've added a discrete amount of momentum to it, and it has a proper energy-momentum relationship. So maybe I should start thinking of these states as particles. Particle with a well-defined momentum that has the right energy-momentum relationship for something like a mass m, right? Can't think of it as a particle in the spatially localized sense, but it's good enough for us to start calling it a particle. So, these some discrete of energy and momentum. So we may as well call it a particle. In non-relativistic quantum mechanics, we call those things quanta. But it's very similar. So we can also do things like following Noether's theorem, we could construct things like the angular momentum operator, and then check what's the angular momentum associated with a state like this, so we can find out that if it's in the vacuum state, then it's really a spin zero particle. Another way to see that it's something, I mean, you can at least check that it obeys Bose-Einstein statistics, just from the fact that it has these sorts of annihilation-creation relations, right? But moreover, it obeys Bose-Einstein statistics. And zero spin. We won't stress that part yet, but we can show that. So okay, so this is sort of the main physical points I wanted to stress in this lecture about, now we're really doing the first step into relativistic quantum mechanics, relativistic and quantum field theory. And now, like always, right, when you're trying some new thing, there's a lot of formalism at first. So we have to do, unfortunately, a little bit more formalism. Because not all, it's helpful for sure to work with Lorentz invariant quantities. We want to exploit special relativity as much as we can. So some of the integrals and conventions that we're used to kind of need to upgrade also to make things, explicitly Lorentz invariant. So one thing we need to do next, talk about the relativistic normalization for these states. So we can choose 0, 0 to be 1. We can choose that normalization. But what about these states, these momentum eigenstates, sorts of things? The obvious guess but what about P? So our guess might be that I take P and I'm just going to do this dot product on Q. Our guess might be that this is just going to be some, seems like whenever we have three delta functions, you have a 2 pi cubed that appears. So I guess a 2 pi cubed, and guess that it's just this Dirac delta function. The difference between P and Q, right? Should be something orthonormal. But, right, I mean, you don't have to think very hard to realize that this is not Lorentz invariant, right? Here I'm talking only about the 3 vector. We know really momentum is supposed to be in this bigger object, the 4 vector. And that's the Lorentz, that's the thing we really should be working with. So right, this isn't Lorentz invariant. This is Lorentz invariant. But let's check. See what that delta function really looks like. So it will suggest how we define the inner product such that it is something Lorentz invariant. So is it clear why we're asking this? I mean, right. The useful thing about inner products, right, is it gives you some way of measuring lengths. Talking about and lengths are things that are sort of the useful thing about lengths is that they're Lorentz invariant, or that they're invariant under some coordinate change, right? That's why we like talking about 5 meters for some object or whatever, right? It's something that's true in all frames. So we want to have something that's equivalent for lengths among our momentum eigenstates. So, right, let's check the Lorentz invariant, or the transformation boundary, I guess, of this delta function. So, right, consider, for example, let's consider a boost in the x3 direction. So how do momentum and energy change? Well, that's from one of last week's lectures. We wrote down how these things rotate into each other, basically, with an angle that's like theta, basically, something like an angle. You have this gamma factor times 2. So basically, Lorentz transformations will mix up energy and momentum between frames. So we want to know right, how does this thing transform under a boost. So we can rewrite, the primes in terms of the unprimes and so on. Like, there's a very helpful formula for delta functions of a function, which I know we did in Shankar, but maybe other people haven't seen it. But we can make use of identity that delta with f of x minus f of x naught is 1 over f prime x naught delta x minus x naught. Where these zeros are right where the function values. So right, it's only going to be going, it's only going to have support around places where the variable is 0, right? Because that's what the delta function looks like. And you can show, if you do some Taylor expansion, you can show that the only part that's going to show up on the right-hand side involving the function is 1 over the derivative of it. So for us, right, we can think of P being some function of the P primes. And so the F prime that's going to enter, so instead of F prime of X, we'll have PT3 or PT3 prime. So that'll be how we evaluate what the, how the delta function transforms under a boost. This that 3 delta function is the prime coordinate, the difference between the prime and momenta. The times now this derivative, 1 over that root. So now instead of pi being on the bottom, time goes on top. So I'm getting 1 over. All right, and so I can find exactly what that is from my Lorentz transformation properties. I find dp3 prime, dp3 will just be right. So gamma doesn't count; he's not used only depending on beta, right? But p3 and also e can depend on the momentum. So I'll have 1 plus beta dE dp3. So I'd like to have an expression for dE dp3. So let's remember too how. So E and P3 are in the same frame, right? So I don't need anything about the Lorentz transformations for them, right? squared is p squared plus m squared. Or in other words, right, this is really a three vector. So I know it's p1 squared plus p2 squared plus p3 squared plus m squared. So I can get the 2e p3. So if I did this derivative, right, we use chain rule basically. And the thing on the right hand side, the only thing that would be left is the 2p3. So I get dE p3 is p3 over e. Right? So I can insert that back into the above. Again, well, the difference in momentum is the difference in the prime momentum and times that derivative, which is just p3 over e. Which is gamma. 1 plus beta p3 over e. And that is actually something that we can find already on the board, basically. So it looks very similar to this e prime quantity, right? But basically, if I do e prime over e, it gives me exactly that. Right? If I just do divide by e, that becomes 1, it becomes beta p3 over e. Exactly that. You get that this is e3 e prime minus e prime over e. Or in other words, when you pull the e over to the left hand side, we get that e times delta function is equal to e times the delta function. So that's the thing that's Lorentz invariant, right? I just saw, when you look at what the Lorentz transformation properties are, just that delta function, and I just get out a e prime over e. So instead, I should just define this as being the thing proportional to the dot product between two momentum states. That's the Lorentz invariant quantity we should work with. All right, this thing is Lorentz. So therefore, we'll define actually, before I wrote that we were defining p as just being equal to n dagger times 0, but we'll actually have a prefactor here, which involves the energy, and also the 2. 2 is up to us, but we choose the 2 because it's convenient for other factors of 2 that will come up later. And right, this implies that the dot product between any two of these will be 2 EP times 2 pi cubed times E3 delta T. Alright, so this is, there's going to be a little bit more formalism at the beginning of next lecture too, but then we'll move on and start doing some more exciting stuff and eventually look at the dynamics. And return to this topic of causality, which we were talking about before. Are there any questions on this or about the homework? Alright, so don't forget the homework due on Wednesday. Let me know if you have any questions about it, if anything comes up.
chance to do telescope.
Yeah.
Did you ever look up? Did you have a telescope to look with at all?
I mean,
Pretty much came down to grumpy kids every night.
Mars, Jupiter, and Saturn will be up for a while.
Okay.
Those are the more interesting ones. Venus is just like you just see clouds.
Saturn is.
Saturn would be cool. But
So this week.
I have lab Tuesday. Tuesday night.
Okay.
So not Tuesday.
Because I teach that class at Dort Tuesday morning, and then I'll be working on homework for Wednesday. And I teach again Thursday morning, so like Thursday night.